Hello students, I am Dr. Anita Sharma. Welcome in my chemistry class. In my previous lecture, I explained outer sphere electron transfer reactions. So in this lecture, I am going to explain inner sphere electron transfer reactions. So without further ado, let's begin. Coordination Chemistry, paper 302. Today we are going to start a new topic of coordination chemistry, that is inner sphere electron transfer reactions. There are some conditions for inner sphere electron transfer reactions. So first condition is at least one complex should be labile in nature, and between two complexes at least one complex should have one bridging ligand. So in this kind of reactions, oxidizing and reducing agents should be in contact with each other, and due to this bridged activated complex is formed between both the reactants, and after the formation of bridged activated complex, dissociation takes place and electron transfer reactions occur. These are few examples of bridging ligands: OH negative, O2 negative, NH2 negative, N2 negative, CO, Cl negative, Cn negative, Br negative, etc. can be act as bridging ligand. In 1959, Tobey and co-workers had done oxidation of chromium second ion from hexaaqua chromium 2+ aqueous complex in acidic medium through reduction of chromium third ion of pentaamine chlorocobalt 2+ complex. Now we will see the reaction of these complexes. So here I have written the reaction between pentaamine cobalt 2+ and hexaaqua chromium 2+ in acidic medium hydrolysis. So we are getting here hexaaqua cobalt and here hexaaqua chromium chlorine plus complex. So what exactly is happening, whether these two reactants are following the conditions for inner electron transfer reactions or not, that we have to see. So we will start with this complex. Here I have written the complex. In this complex, cobalt is in +3 oxidation state. Here you can see cobalt, the oxidation state of cobalt is +3 because here +2 is written and 1 plus is cancelled by Cl because Cl is -1. So the oxidation state of cobalt is +3. NH3 is a strong field ligand. So if the NH3 is acting as strong field ligand, the configuration will be D7. And since the configuration is D7, because when you will write the electronic configuration, you will get in +3 oxidation state, D6 configuration will be there. So D6 configuration, and due to this D6 configuration, all 6 electrons will enter into T2G orbital due to presence of this NH3 strong field ligand. No electron will enter into EG orbital, and as I have already explained in my previous video, the condition for a complex to be inert, if 3 or more than 3 electrons are present in T2G orbital and no electron is present in EG orbital, then complex will be inert in nature. So this complex is inert, but the condition is at least one complex should be labile in nature. So here you can see this complex is inert in nature. Now second complex which is taking part in this reaction is hexaaqua chromium 2+. So in this complex, chromium is in +2 oxidation state and H2 is a weak field ligand. So D4 configuration will be there, and since H2 is a weak field ligand, the electronic configuration, 3 electrons will enter into T2G orbital and 1 electron will enter into EG. Since electron is present in EG, the nature of complex will be labile. So first condition fulfilled, at least one complex should be labile, so this complex is labile. And second condition, at least presence of one bridging ligand. So here Cl is acting as bridging ligand. So now we will see the mechanism of this reaction. So in reaction mechanism, you can see here we have two complexes. This complex is having bridging ligand, that is Cl, and this is labile complex. So when they will react with each other, first they are forming a bridging complex. So this is bridged complex. Cl is acting as bridged. Now in this complex, since this complex was labile, so labile complex, unstable complex, one H2O molecule will be removed. So one H2 molecule is removed from this and we are getting this here. And due to formation of this bridged ligand, the oxidation states changes. Now here it is +2 and now the oxidation state of chromium is +3. So in this particular complex, D7 configuration will be there, and for D7 configuration complex always will be labile. And here the configuration is D3. So for D3 configuration always complex will be inert. So now if this complex is labile, this will dissociate. So this Cl will be removed from this compound. So we are getting this. Now we are getting one stable complex in product, but this is not stable complex. Why it is not stable? Because it is not coordinatively saturated. Here NH3 5. So on hydrolysis we are getting this compound. One H2 molecule will attach here. And on further hydrolysis, which is rapid hydrolysis, all NH3 molecules which are ligands, which are acting as ligand, will be replaced by H2 molecules, and finally we will get this compound. So by this reaction of one labile and one inert complex with one bridging ligand, final products which we are getting are these two. So finally, one more time we will discuss the requirement of ISM, Innersphere electron transfer mechanism. First, in this mechanism, a ligand is shared between reductant and oxidation in their inner coordination sphere. That shared ligand is called bridged ligand. The attachment between oxidant and reductant occurs through a bonding ligand. That is also known as bridging ligand. One ligand of one reactant must be substantially labile. Therefore, it should be capable of getting replaced by a bridging ligand in an easy substitution process. If a complex is labile, then and then only it will dissociate and its ligand will be replaced by bridging ligand. The rate of inner sphere mechanism, this is important point, the rate of inner sphere mechanism is more than outer sphere mechanism. So these are some references. This is all about inner sphere electron transfer mechanism. Thank you.